Hello, welcome back to Astronomy 305, Life in the Universe. We are on module C2b, which I believe is called Modern Science. And I hope so far that you enjoyed our history story of science and how it related to astronomy, or how astronomy was key in developing our sense of how the universe works, and a methodology for how this science as a discipline works. Human creative process that we've slowly developed over the last few centuries. And it's been extremely powerful. And what I hope to do in this next topic is to discuss with you how powerful it really can be, because whereas everything that we learned before from Aristotle, say through the Copernican revolution and the work that Galileo did, that was all very clear, observable information that, how a body falls, how the planet moves. These things were directly observable. There was nothing that was sort of beyond the human sensory experience. And the thing that is important, I think, to realize is that science has become so powerful that it's been able to extend well beyond the five senses, the experiences of everyday human life, and uncover things about the universe with quite good certainty, okay? And of course, we continue to make our point that no theory is not without its incomplete components, because as we probe deeper and deeper into nature, we always find more things going on than we had previously suspected. So going back to our previous lecture, we had learned about the geocentric model from Aristotle, a very, very directly intuitive picture put together by the human mind based upon the motions of the stars and the planets. And then the refinement of that through Ptolemy, making loop-de-loops in his little spheres and whatnot to undercover retrograde motion of the planets. They would go across the sky and then turn around and come back. They don't really do that, as we learned, but they appear to have that motion on the sky, and that was a tension on Aristotle's model. So anyway, Copernicus said, let's move the sun to the center, let's have a heliocentric model. He was able to naturally explain that retrograde motion without having to create the planet doing loop-de-loops out there in space. And we went from there to Galileo, who invented the telescope and put the last nails in the coffin of the Aristotelian geocentric model, phases of Venus, moons of Jupiter, sunspots. And so we're at this stage now where Galileo had developed this experimental method, became the father of science, to actually do experiments that you could write up and show other people how you did them, and then they could repeat them and they should get the same results. And you got some numbers back out that would tell you exactly, well, gosh, if I drop a ball, it falls 9.8 meters in the first second, and then the next second it has traveled to almost 20 meters in the next second. And in the next second, it's traveled almost 30 meters. And so it's picking up speed as it falls. That's called acceleration. But there's an exact relationship from 1 second to the next, how it's doing that. And so then we have to scratch our heads and say, can we explain why those numbers are what they are? So what today I want to do is tell you is that something that is permeates our existence, that we're embedded in, that is space and time, that we're going to talk about a revolution in science which blew our entire concepts of what space and time are away and developed it into a space-time. And so that's the first thing we're going to talk about. The second thing we're going to talk about is this revolution that came from just studying how bodies fall. So it's not a very good thing to do, but here's my pen, if you can see that in this virtual landscape. And then if I drop it, sorry about that, a little loud. We see that every day. And 99.99% of us don't think about it. It's like, oh, there's gravity and things fall to the earth and big deal, I'll move on with my life. But as scientists, they're like, why is that happening? How is that happening? What's behind it? And it turns out that trying to answer that simple question caused a revolution in physics with Aristotle. It caused a revolution in physics with Galileo. And then it caused another revolution with Newton that helped him define gravity and Newtonian gravitational model. And then it helped Einstein. I'm going to show you about a thought experiment he had where he was just thinking about how does a body fall in a gravity field. And he revolutionized everything. And I'm going to talk about that as well. So let's get going with that. I'm going to go ahead and share my screen and get my slides going here. Let's see, I seem to be having a little bit of a problem here because I've got things on multiple desktops and I can't get my screen again. So this is not good. I'm going to pause this. Okay, so I'm back. I'm sorry about that little debacle, but I think I got my act together now. Okay, great. Thank you for your patience. So here's our first slide for today. And we're going to move on to modern science, or at least some of it, because we're not going to get into the whole revolution of quantum mechanics. But anyway, the first revolution is going to be of space and time. And this is ushered in by Einstein's theory of special relativity. Please don't step on my keyboard. And there was this 3,000 year, pardon me, I've got a friend. There was this 3,000 year paradigm that existed all the way from Aristotle, and it was adopted by Galileo and then adopted, we'll see, by Isaac Newton, that space and time are rigid, that they're absolute and unchanging, and that should sound familiar with you from the days of Aristotle. And they were replaced with a space-time continuum in which space itself is pliable and time itself is pliable, but the continuum itself is basically not. The relationships between space and time form sort of a geometry, if you will, that is set. Okay. The second one is the revolution of falling bodies that I mentioned. This ushered in Einstein's general relativity theory. You might be, what's all this relativity stuff? But we'll talk about that in a little bit. And so you'll notice that this is a theory of gravity, but the theory doesn't have the word gravity in it because it's so much more encompassing. Anyway, from the time of Newton, it was about 300 years since he had put together his theory of gravity. And so there was this problem called action at a distance that people didn't understand, which I'll go into. And that's basically they didn't know how the force of gravity was actually transmitted from, particle 1 to particle 2, or Earth to the sun, or moon, or whatever you have. And so basically, he got rid of the idea of a Euclidean, if you will, normal X, Y, Z kind of space that you're used to seeing, up, down, and left and right. He developed something called a curved space-time. Sorry, I'm being distracted because I got a little kitty cat here who wants to lay on my lap and wreak havoc by typing on my keyboard. So he basically developed something called a curved space-time, and in doing so, eradicated any need for a force that we know as gravity, okay? That objects now just follow so they follow straight lines and move in constant speeds along the curvature of space-time. And okay, what does that even mean? Well, here's the point that we're going to walk away with. This very weird picture that revolutionized our understanding of space and time and gravity also revolutionized our entire picture of the universe. And I'm at the end of the lecture, toward the end, going to bring up a litany of predictions that we never even could dream of or think of before Einstein developed this theory. Okay. Mind you, we will not be discussing another revolution which happened in the 1920s, which is about 5 years after the theory of relativity came out. This came out in 1915. And that is the revolution of quantum mechanics. And it turns out that that revolution actually taught us about some flies in the pudding, if you will. That's my little comment, my little phrase for saying that the theory is not correct about certain very, very minutely detailed things. And it's those little minute details that where a theory breaks down that show us where we need to go next in our developing our new theories. And it turned out that quantum mechanics pushed on Einstein's theory of general relativity quite hard. And so we know that even this amazing theory, which has basically almost every prediction it has made has come out correct. Every prediction it has made has come out correct, but quantum mechanics has shown us that there are things out there that the general theory of relativity cannot even predict, and therefore it must not be complete. Okay, so let's move on to our story. We're going to start by talking about two gentlemen from the 1700s, late 1600s, that is Isaac Newton, and from the early 1800s, and that's James Clerk Maxwell. So our story so far had led us up to Galileo, and Galileo did a lot of experiments about how bodies fall and things like that. And you saw that Kepler obtained his two laws of planetary motion, but nobody understood why those planets move those ways. And even though Galileo had studied falling bodies, he still didn't know. He was able to talk about how they fall, but he didn't have any theories or ideas, what's driving that motion. Come along, let's go back to the late 1600s with Isaac Newton. And he's at Cambridge, University of Cambridge. He's about 20, 22 years old. An epidemic happens. What do you know? Sound familiar? And so he gets sent home from school, and he's at his parents' farm, and he has a lot of time on his hands. And so I don't know what you're doing with your epidemic time, but he decided to figure out why bodies fall, and he knew that he couldn't figure that out until he had developed some mathematics that could describe how forces work and how velocities change and accelerate and things like this. And so he invented calculus. What the heck? Okay, 22 years old, home for the plague. Let's invent calculus. And then let's figure out some things. And you'll hear some stories about falling bodies. And he thought about an apple, how it fell. And then he thought about how the moon stayed in orbit. And he tied them together to the same phenomenon, and he called it gravity. And in the end, he developed laws of nature, 3 of them. The most famous one is F equals ma, so force equals mass times acceleration. And the force of gravity is basically a special version of that, in which the acceleration turns out to be the Earth's mass divided by the mass of the Earth squared. Radius of the Earth squared, sorry. The mass of the Earth divided by the radius of the Earth squared, and then multiplied by a constant he called g. So g times mass of Earth divided by radius of Earth squared. is the acceleration on Earth. And then if you have a body, m, like me, and you multiply it by that product I just told you about, g times mass times over divided by radius squared, you get my weight, okay? And so that was the brilliant insight that Newton had. He also was able to calculate how long it should take the moon to go around. And get this, after he formulated all his motions, F equals ma laws and stuff like that, he did a lot of calculus and a lot of heavy duty math, and guess what popped out the other end? All of Kepler's laws. So from mathematical principles and just understanding these three laws of motion and applying the math to them, he was able to derive in like a one page of equations all of Kepler's three laws. Now that is a crown jewel achievement for any scientist, but that was just, you know, one of the cherries on the tree for Isaac Newton. It goes on and on and on. But the thing that was interesting was that he put together a system of equations for understanding motion. And we're going to talk a little bit about that. They firmly believe that all motions were then all set in stone because they followed the laws of physics. And here's a very interesting thing, and it changed our picture of the universe as well. He basically said that, geez, if the creator of the universe had put all the particles in their positions and gave them all a velocity, so a direction and a speed, and then said, go, universe, go, and they would all follow the three laws of motion, according to Isaac Newton, the rest of the universe is predetermined from then on. Everything is just going to go through time and follow those laws of motion. And that really was a new thought in a sense. I've got it here in green. Once the positions of velocities are particles in the universe are initialized by God, and he spoke of God right next to a science. That was, back in those days, they were called natural philosophers. Then the forces cause the universe to unfold, or I should say the laws of motion cause the universe to unfold in a manner completely predetermined. And so we started renaming the universe the mechanical universe. It was all mechanical, it just followed these mechanics. And this is the kind of stuff that led to our industrial revolution. It led to understanding economics in terms of mathematics. It really changed and transformed everything. And in fact, people thought there really might not even be human free will because all our particles were set in motion and we follow Newton's three laws. Therefore, we all have predestinies and there's no free will. So there was a lot of philosophical dialogue generated from this, and it affected economic and political systems. And it's very important to understand that sometimes physics can have that effect on our society. Okay, and then we're going to talk about James Clerk Maxwell. And James Clerk Maxwell, he lived in the early 1800s. When he was a young kid, also in his 20s, he decided that electricity and magnetism seemed to behave as if they were one and the same, or different expressions of the same thing. So he put together 4 equations. They're beautiful. Maybe you've seen shirts and God said, and there's these 4 equations and there was light. That would be Maxwell's equations. They describe everything you know about electricity, everything you know about light is described in those equations. So, you know, the fact that we have light bulbs today, the way they behave, the way electric circuits behave, the way electricity is generated in generators at, say, hydroelectric plants and then sent across the country, all of that came out of these 4 equations. Okay, so this is a very, very amazing time in our history that we developed this kind of information. Now, there's one thing that really, after Maxwell finished, caused some tension. with Newton's theories, okay? And whenever that happens, one has to scratch their head and say, well, who's right? You know, is Newton right or is Maxwell right? Or are both of them right? And we just can't see it. And so that's a beautiful thing for scientists. They love to be in that situation. So what are those two things? They're down here in the black on this slide. Newton said that the velocity you measure of something depends on the velocity of the observer as well. And I'm going to get into that in a little bit, okay? So the problem is that Maxwell said, not with light. Light travels at a constant speed. And it doesn't matter how you move relative to your flashlight, whether you're moving with it or you're moving toward it, the light comes at you or moves away from you at the speed of light, 300,000 kilometers per second or 186,000 miles per second. So if your intuition tells you, like, if I'm going toward a car that's coming at me at 60 miles an hour, it's going to appear to be coming at me faster. You know, like, that's why you don't want to be in a head-on collision, okay? Because you basically are adding the two velocities as they come together when you collide. But that wouldn't be the case with light. If you're coming toward a light beam, you're still coming toward it at the speed of light, or it's coming toward you at the speed of light. So how can that be? And that turns out to be one of our major paradigm shifting revolutionary moments. So let's go into this just a little bit detail. I got one slide on Newton and I got one slide on Maxwell, and then we're going to move into Albert Einstein and how he glued all this tension together. As with all science, when you put together a theory, it has to stand on some assumptions or some pillars or what we call axioms or postulates. So let's talk about Newton's postulates. Okay, first of all, the laws of physics are the same for all observers. Okay, doesn't matter who you are, where you are, how you're moving, when you are in time, laws of physics are the laws of physics. Okay. Time is a universal phenomenon. It's the same everywhere and every when. It never changes, and it's the same for all observers, okay? And that's very Aristotelian if you think about it. Space is universal. It has 3 dimensions, okay, X, Y, and Z, if you will, and that means it's Euclidean. Those 3 dimensions that I'm talking about, that's from the Greeks, Euclidean. And it's the same for all observers everywhere and every when. So space is space, time is time, and the physics are the laws of physics. It's no reason not to believe about that. It seems pretty good, right? All right. So again, once every object's position and momentum is known, momentum is its velocity basically, then applying Newton's laws of motion, every object's complete past and complete future can be calculated. I mean, you can run the universe. If you could measure the position velocity, according to Newton, you can measure the position velocity of every particle in the universe, then you could run it backward using Newton's laws. You could run it backward in time and come to the beginning of the universe and see how God had set the universe into motion. Okay, that was some powerful stuff. And like I said in the previous slide, that created a whole new worldview, okay? Including the idea that there's no free choice for humans. We have predetermined fates. We clearly don't believe that anymore, and we're able to justify that now because of Heisenberg's uncertainty principle in quantum mechanics. So yay, quantum mechanics. Okay, so what about this James Clerk Maxwell fellow, which I'm showing him as an older man, but you know, there's lots of pictures of him as a young type looking just like you guys do. Okay, so it turns out that his laws of motion for light don't obey Galileo's and Newton's relativity. Okay, so what is he standing on? He's standing on 2 statements. Or I should say he's basically standing on Isaac Newton's 3 postulates. He adopts Newton's 3 assumptions about assumptions about space and time in physics. And through that, he was able then to unify electricity and magnetism into this single phenomenon called electromagnetism. So what am I showing you here? On the left is basically a modern version of what we think a light beam looks like. It's a cartoon, but it's basically comprised of an electric field and a magnetic field. The electric field is an oscillation wave that oscillates in this plane, and the magnetic field is a wave that oscillates in the vertical plane. And it turns out that as this field changes in its strength, how far out it is from this line it's traveling along is to represents the strength of the electric energy and the strength of the magnetic energy. And it turns out that as the electric energy changes, it causes a change in the strength of the magnetic energy. But as the magnetic energy changes strength, it causes a change in the electric energy. And so you get this circle here called changing electric fields produces changing magnetic fields, which change and make changing electric fields, on and on. And so you get this propagation. It's like a self-propagation between electricity, magnetism, go to blah, 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 blah. And it does that at the speed of light along this direction, okay, the direction that the wave is traveling. So that's basically what a light beam is. And then there were some constants that he had to come up with to get an understanding of how it did this. And he said, well, I'm going to say that it does this in something we're going to call free space, basically a vacuum. And I'm going to develop some concepts called the permittivity of space and the permeability of space. And the permittivity basically is telling you how well the electric field can move up and down in space. And the permeability of space is telling you how well the magnetic field can move up and down or get in strength and low and high strengths in space. And it turned out he was able to show that the speed of light could be written down as the square root of 1 over the product of these two things. Now, this is a constant about space, and this is a constant about space, and you multiply them together, divide them into 1, take the square root, and voila, you get the speed of light. Now, here's what I want you to realize. Okay, and that speed of light is about 300,000 kilometers per second. So that's what this box is saying. Self-propagating wave of electromagnetism. Speed is dictated by permittivity and permeability of space. 300,000 kilometers per second. Okay, now here's what I want you to understand, on a qualitative level. If you look at that equation, C equals this stuff, the stuff only is about space. It doesn't say anything about a person or what they're doing. It doesn't say, oh, at time such and such, there's no t in the equation. It doesn't say at such position, like there's no x, y, or z in the equation for where you are in space. And there's no like, oh, if you're moving this fast or not moving this fast, there's no motion of the observer. You don't see a v, which we usually in physics we write that as a v. Here's v, that would be the motion of the object or the motion of the observer. There's nothing like that. There's no time, there's no x, y, z, there's no velocity. It's purely, that's what light does, okay? It's permittivity, permeability of space, that's what light does. I don't care anything else, that's what it does. And so that's the prediction. The prediction is the velocity of light is the speed c, 300,000 kilometers per second. And that's it, folks. There's no more to that story, okay? So that means that the velocity of light, even in a moving system, must be the velocity of light. So if I'm shining a flashlight coming at you, I see the light move away from me at the speed of light, and you see the light coming toward you at the speed of light. It's a lot different than if I was throwing a ball at you and I'm coming at you at 100 miles an hour and I throw the ball at you at 100 miles an hour. You can do the math. It's coming at you at 200 miles an hour, but it's leaving my hand, from my perspective, at 100 miles an hour. Light doesn't do that. So that's what the next slide is all about. Fast forward to about the 1890s when Albert Einstein was, about 16 or 17 years old. I mean, get this. I mean, all these people are kids when they do this work. It's amazing. Okay, Albert Einstein, high school, bored to death, can't stand the place, you know, getting bad grades. Why? Because he's thinking about the big stuff. Okay. Uh, okay, so 1890s, he's like, I'm confused, and I'll talk about his confusion in a minute, but let's go through this, the two things that are contradicting each other, this top panel and this bottom panel. Okay, excuse me. So here we have a train. It's going 100 kilometers per hour in this direction. And we have an observer standing on the ground, not moving at all. Okay, they both shoot an arrow, and the arrow leaves their bows at 200 kilometers per hour in this direction. Okay, we've already done this, right? This one goes at 200 kilometers per hour and hits this target. This one leaves the bow at 200 kilometers per hour, but the bow and the person are moving at 100 kilometers per hour. So add them together, and this is moving from this guy's perspective, or this young lady's perspective, is moving at 300 kilometers per second. So we're going to call this person A and this person B because we're boring. Actually, we could call them Alice and Bob, but I got the genders backwards. So Bob is really Alice and Alice is really Bob. Okay, so Alice and Bob both shoot their arrows at 200 kilometers per hour from their own bows. Alice sees his arrow or her arrow go 200 kilometers per hour. See, here's Alice, and Alice sees 200 kilometers per hour from Alice's perspective. Alice also sees Bob's arrow go 100 kilometers per hour. Why? Because, well, it's going 200 kilometers per hour, but Alice is moving at 100 kilometers per hour, so she has to subtract the difference off. I got the genders backwards, but we'll work with it. Okay, what does Bob see? Bob sees his arrow or her arrow go at 200 kilometers per hour. And Bob sees Alice's arrow go at 300 kilometers per hour, as we were talking about, because Alice is moving at 100 kilometers per hour. Her arrow is already moving at 100 kilometers per hour before she launches it at 200 kilometers per hour. Now going, according to Bob, 300. Okay, now let's talk about them. Let's give Alice and Bob some laser guns. Okay. Okay, so here's Alice and Bob. Alice has to go a lot faster to make this work. So we're going to say that Alice is going about half the speed of light on her train, you know, pretty quick. So let's say she's going, oops, that's supposed to have another zero there. Let's say she's going 150,000 kilometers per second. And right when they get equal, okay, Alice and Bob fire their lasers. And what the Alice and Bob both fire their laser guns, and the light travels at 300,000 kilometers per second out of each of their laser guns. Okay, just like the arrows both traveled at 200 kilometers per hour. What does Alice see? Alice sees his or her beam going out at the speed of light. Okay, Alice sees Bob's arrow, beam going at 300,000 kilometers per second. Yeah, that's supposed to be beam. I try, people. I make mistakes. Okay, so basically, Alice sees her light and Bob's light going at the speed of light, and Bob sees his light and Alice's light going at the speed of light. See, it's a very, very different situation. And so you have to ask yourself, how can that be? Okay, so that confused Albert, okay, because really, according to Newton, Alice should see Bob's laser going 150,000 kilometers per second, because it would leave at 300,000 kilometers per second, but Alice is moving at 150,000, so 300 minus the 150,000, it would only be going 150,000 kilometers per second to Alice. So, yeah, and conversely, Bob should see Alice's light beam going at 450,000 kilometers per second, which is the speed of light that it left the laser gun from, plus 150,000 kilometers per second that the laser gun is going when it shot the light. And but that's not what they see. Again, they both see the light go at the speed of light, 300,000 kilometers per second. So how in the world could that be? Something's got to give. Something's got to bend. Okay. Okay. So let's summarize. Whoa. So Newton and Galileo say that the speed of the arrow I measure depends on how fast I'm moving. Okay. Bob not moving. Alice moving. People moving at different speeds measure arrows moving at different speeds from each other. Yep. Intuitive, makes sense. Okay. We experience it every day. But Maxwell, when it comes to light, says it doesn't apply to light. No matter how fast you are moving toward or away from a light source, the speed of light is the same. All observers always measure the speed of light to be 300,000 kilometers per second. And experiment bears this to be true. Okay, you do any experiment, you measure the speed of light, you always get the speed of light. Okay, so Maxwell's right. And for non-light, Newton and Galileo are right. Okay, so how can this be? This is what we call a fly in the pudding. This is the stuff we love. This is the stuff that says, we've got some work to do. We're gonna learn some stuff here, okay? So that's the kind of stuff we like. So it takes a special mind, okay? And that special mind belonged to a young man by the name of Albert Einstein. So this is what Albert Einstein did, okay? There's tension between Newton's picture of relativity, how they call that relativity, the adding of the motions, you know, whether you're moving and they're moving or not moving, that, you know, and the relative differences that you see. And Maxwell, okay? And at age 16, Einstein had this thought. If I travel at the speed of light, you know, we had Alice moving at half the speed of light, but what if we put Einstein on Alice's train and we make Alice's train go the speed of light? XYI, or FYI, sorry. This is before Albert Einstein ever had figured out that nothing can go the speed of light or go faster than the speed of light. So it was a legitimate thought at the age of 16. He hadn't yet written the rule that said you can't do that, okay? In fact, it's this thought experiment that made him realize you can't do that. All right, here's what he thought at 16. If I travel at the speed of light in the same direction as a light beam, Newton says I should see the light standing still. I'm moving with it. And I should be able to watch those electromagnetic waves do their thing right in front of me. And he realized that was impossible. Okay, so Maxwell says that can't happen. All right, so he went with Maxwell. Okay, he went with Maxwell. He went with the experimental data that always measured the speed of light to be the same. So he's like, I got to go with that. So he made two postulates that he grew his theories on. Number one, light is a constant speed for all observers. Okay, he just takes the rules that came out of Maxwell's unification of electricity and magnetism and says, I'm going to embrace that. And then he embraced Newton's major law, which said, major postulate, which is that the laws of physics are the same for all observers. So he took the first one from Newton and he took the law of constant speed of light from Maxwell, and he said, now, what happens if I work everything out from there? Okay. And so he worked out some situations, and I've got some really good movies that you really have to watch or you'll never understand this stuff. The lecture is helpful, but it doesn't describe it visually and with video and motion that these great YouTube videos that have been put together, or at least they've been dumped on YouTube now, but they were developed by universities, Einstein discovered something had to give. And what he found out had to give was that space could not be just absolute and the same for everybody for all time, and that the way you define time, the passage of time itself, could not be the same for everybody. Okay, so let me read what I've got here in the blue. He finds time cannot be a universal constant. It depends on both the observer's velocity and the distance from the time measuring devices. Okay, So it's not a constant throughout space. You can measure time further away from you or closer to you, and you'll find out that it's passing at different rates. I know. Also, he finds that space contracts or expands depending on your motion. Okay, weird, okay. But it turns out that it's been experimentally verified time and time again. And in fact, you probably heard of the Higgs boson and the discovery of these particles and these particle accelerators. Maybe you have. But all of that stuff is based upon the fact that time and space are not constant. In order to do those experiments, you have to adjust all your machinery for these facts, or they don't make sense at all. It doesn't work. Okay. So moving on, let's summarize special relativity. Great, another misspelling. You're welcome. That should be relativity. Assumptions. We covered this already. I'm just recapping them. Speed of light is the same for all observers, and the laws of physics are the same for all observers. Do some math, do some calculus work that Albert Einstein borrowed from Isaac Newton. And then what were his conclusions? Time and space are not the same for all observers, but it turned out something called space-time is, okay? If you observe a clock that's moving, it is ticking slower. It's not a mechanical thing. Time is dilated, okay? And if you observe a ruler that's moving past you, it is shortened. And that's not a mechanical thing that happens to the ruler. You are actually observing the space from its point of view is smaller. The space from your point of view for the moving object is smaller. Okay. So for the win, I want you to go watch the two videos on special relativity. I think one of them is just called Relativity, and the other one's called Space-Time. Now the one on relativity is just going to show you a little bit about why time gets dilated for a moving clock. It's really good graphics, really good explanation. Give these videos their due, just relax and watch them. And then the space-time one, it's a little longer, it's about 10 minutes, and it gets into describing something called the space-time diagram. This is probably the only time you'll ever really look at this stuff in your life, unless you become some kind of armchair physics person when you get out of school, or already are such a person. But the space-time diagram is basically a small graph that basically has space along one axis and time along the vertical axis. And so a point being plotted in different locations on this graph is at different places in space and in time. And it turns out that you can, when you plot a point at some spot on the graph, it's the here and the now. And then you can talk about the future and you can talk about the past. And it turns out that a line that's at an angle tells you how fast that particle or how fast that thing is moving through space and time. And so a light beam, which moves at the speed of light, 300,000 kilometers a second, always moves at these right angles from each other. So a light beam moving in space to the right, forward in time, moves along this line from one moment to the next. And in the past, it came from over here, and then earlier in time, and moves up to the here. So you can look at everything not as a here and the now, but you can look at things within the context of where they, as events in space-time. So an event is something that has a here and a now. It's a point on this diagram. So listen, many of you are working very hard to put yourself through school. Many of you might be taking out student loans to put yourself through school. You are spending an awful lot of money to listen to me talk right now. And you can either get and extract as much of the worth out of this all. In other words, get your money's worth. Or you could say, I'm just not that curious about science and I'm not going to look at it and I'm just going to get the minimum points and not get your money's worth. Okay. Yeah, you get your piece of paper, but really why you're here, and I'm sorry for the soapbox, is to learn. You'll never probably look at this stuff again. So you know what? If you have the time, and trust me, as you get older, you have less and less time. So now you probably have more time than you ever will in the future. Look at this stuff. Get your money's worth, because someday when those student loans come due and you're paying a lot of interest on them, you're going to be paying factors of 2 to 3 of what you borrowed to pay for this piece of paper you're going to get at the end of your education. Take the education and get your money's worth. Don't skate through, okay? And I'm saying that because so many people are like, I don't want to learn about physics. I don't care about space-time. You know, knowledge is amazing. The human mind has done some amazing things in the last few thousand years, and it's going to continue to do that. And if you want to be on the curve of that and be part of that, what's happening in your future, you got to put it up here, and now's the time. So watch the movies is my recommendation. Get your money's worth. Someday you'll look back and go, gosh, if you chose not to do it, you really didn't get much out of college, and man, 25 years paying that student loan, blah. Okay, moving on. Let's get even weirder. Okay, let's talk about the story of gravity now. So we talked about the relativity. We talked about the motion of particles or baseballs or arrows and trains, okay, and the motion of light. And we found out that space and time had to be put together in a continuum, and that time can be dilated, could seem to pass more slowly for moving objects, and their space can seem to be contracted. Okay, excuse me. So what we're going to do now is talk about gravity and the force of gravity and these kinds of things. And you'll remember that I started out talking about Isaac Newton inventing calculus and developing his F equals ma, force equals mass times acceleration law of motion, and applying that then to falling bodies and coming up with this law of gravity. So we're going to talk about Newton's gravity. It's very important if you're going to take an astronomy class that you have been introduced to gravity, because gravity is a force that permeates the entire cosmos and is extremely important for why the universe, is important for constructing the universe the way it is today. Okay, so here we go with our astronaut again, who is floating in space. No, not so much. They're experiencing a force of gravity downward toward the center of the Earth, and the Earth is experiencing a force of gravity toward our astronaut. Okay, they both pull on each other equally. Pull, what with? Do you see a tether? Do you see anything that's transmitting that force? That's kind of the problem here. The strength of that force is going to depend upon, how massive the planet is and how massive the astronaut is, and then how far away they are from each other. Okay. So here's my little stupid kindergarten cartoon that sort of sets up where we're going. What is the physics behind falling bodies? Because really, again, that's the question. In a sense, that astronaut is falling through space. They're falling toward the center of the Earth, but it turns out that they're also moving sideways at a fast enough clip that they never actually come down onto the Earth, because the curvature of the Earth is falling away from them. By the way, you can't do that, flat earthers. If you want to talk about flat Earth models. So what is the physics behind falling bodies, our one person says. And so our smart person says Newton's gravity. because I bet you almost all of you could answer that question. Newton's gravity. Okay, what's gravity? And you might go, it's a force, right? And yeah, I got this. That's a force. I got this. A force. Okay, so our question is a force. What's applying the force and where is it? That's what killed Newton. He could never answer that question. He could formulate the math, he could call it a force, but he never could figure out what it was. Okay. And so, okay, a little embarrassed now. The center of the earth, the center of the sun, the moon, the center of the moon, the center of the object, whatever. Okay. And so the question now is, but how does the center of a planet apply force? Well, I think you'll agree that that doesn't make any sense. Okay, so, mind blown, end of conversation. And this is really what happened to Newton. And he was so stymied by it that he basically said, I'm going to leave it as an exercise to the reader to resolve this, knowing that someday, maybe 300 years later, somebody, maybe Albert Einstein, would come along and solve the problem. Okay, so this was his problem. He called it magical action at a distance because the force seemed to be instantaneous. It seemed to reach instantaneously across space, that the force on the Earth from the sun seemed to reach instantaneously across space and pull on the Earth, but there was no transmission that could be seen. And the speed of the transmission, it seemed it had to be instantaneous. Not that it traveled at some finite speed and took time to get from the sun to the earth. Okay, we're going to find out that it does take time, whatever it is that's being transmitted. It does take time. It moves at the speed of light, this transmission of gravity. And we're going to find out that it's really not a force. Okay, so let's move on with that. Okay, so what is Isaac Newton's gravity? Isaac Newton's gravity is basically a force, quote unquote, between two masses. So here's a configuration of two masses, say mass 1, which could be like the Earth, and mass 2, which could be, say, like the moon, or this could be our Earth, and this could be our astronaut. And so the force between them, gravity, is equal and opposite to both. Okay, what does that mean? That means the force that mass 1 is attracting for mass 2 with is equal to the force that mass 2 is attracting mass 1 with. So they both feel the same force towards each other. Okay, so that's why we say F1 equals F sub 2. Okay, and that force is basically the product of the masses, the mass of particle 1, the mass of particle 2, divided by their distance square measured from their centers. And you take that quantity and multiply it by this constant g, if you will, and don't worry about what g is, it's just a number that makes things work out. And you get the force of transmission, force of gravity between them. In a sense, why does an orbit work? We'll look at this diagram here. You could think of the sun and the Earth, or you could think of the Earth and the astronaut, and give it a picture of it at one given time. What's acting on it according to Newton? According to Newton, the planet is moving along the arc. It's at this instantaneous second is moving in this direction with this amount of speed. And at that instantaneous moment, it has a force acting on it from the sun that's directly toward the sun. So it's important that you realize that the force always acts directly on a line between the two masses. When you couple the fact that this mass wants to pull this planet inward, but the planet's moving this way, it turns out that the planet will move this direction. And then at this point, the force is pushing it toward, pulling it toward the sun. The motion is wanting to move it this way, and it then moves this along that arc. And so you get this balance between the motion of the planet and the force on the planet that cause it to go around in the orbit. It's showing a circle here, but as you know, it can be an ellipse. Okay, so it turned out that once Newton formulated this equation, he was able to derive all of Kepler's planetary motions, which I told you before. And he found out that planets orbit the ellipses, and they have constant angular momentum, which, if you remember, was Kepler's second law, that they sweep out equal areas in equal times, because when they're closer to the center object, they move faster along their arc of their orbit path, and when they're at their farthest point, they move slower. Okay. So this was Isaac Newton's picture of gravity. And here's another sort of picture of that with a graph of showing the strength of the force. Again, you have mass 1, mass 2. You have a distance r between them. Mass 1 pulls on mass 2 pulls on mass 1 with the same force that mass 1 pulls on mass 2. The product of their masses divided by their distance squared times this g gives you that force. Here is the force in some arbitrary unit, and here's the distance in arbitrary units. So if the distance is 1, and we say the force equals 1, we just arbitrary numbers, what we're showing is that if you go twice as far away, the force becomes 1/4 of what it was. And if you move 3 times farther away, it becomes 1/9 of what it was. If you move 5 times further away, it becomes 1/25. This is the inverse square behavior. We're going to see that law again a little later in the class when it comes to light. This is called inverse square behavior, or an inverse square law. And so if you double the distance, the force goes down by 1/4. Basically, you double something, that's 2, you square that, it's 4, and then it's divided by the 4, so it becomes 1/4. Okay. In the end, we have to ask these questions. What transfers the force? How fast does the force communicate between the two masses? And how does the gravity work? Basically, these two questions. And Newton never could figure it out. He called it action at a distance, and it troubled him deeply. And it turned out that it stuck around, that problem stuck around for 300 years until Albert Einstein came along and said, it's not a force, it's something entirely different, okay? So this is one of those flies in the pudding. It stuck around. A lot of great thinkers thought about it. Nobody could come up with anything. And Albert Einstein just saw the world so differently that he had no problem with it. Okay. All right. Now, what I want to do is get you to refresh your mind. This might be a good time for you to take maybe a little break. I don't know how long you've been listening. It's good to take this stuff in parts, but we're going to move now into stuff that is very, very strange and very different, and it's going to require a bit of explanation. So get yourself freshened up, get yourself a new cup of coffee, and come back here and you can finish off. Okay, so there was, as usual, some things that got observed out there in the solar system or whatnot that could not be addressed by Newton's theory of gravity. It just simply was unable to address the situation. Now, I'm going to simplify this a lot, but it's very interesting. What I want you to understand is that Isaac Newton's laws of motion and his theory of gravity are so good that we can use them for everyday things, like launching rocket ships, putting satellites into space, sending humans to the moon and having them land on it, sending spacecraft to Mars, sending spacecraft to Pluto, okay? All of this is done just with Newton's laws. You hardly ever need to go to a more accurate theory than Newton's laws. Just to tell you that basically Newton's laws are extremely accurate. But our measurements are so good that we can go beyond the accuracy of the mathematics and predictions of Newton's laws. Okay, so that's really important. That's how progress is made. We develop the technology to, whenever we have a breakthrough in technology, to make more precise measurements, that we are able to measure things that are beyond the precision of the predictions of the theory. And so one of those things happened in the late 1800s, in that people were able to measure the position of Mercury's orbit with such accuracy that they found it was doing some things that were not predicted in Newton's theory of gravity. Okay. Now I'm gonna tell you a very simplified situation that if you look at this left diagram here, this is the sun, and then this is Mercury in its orbit, and it's obviously an ellipse, and I would say this is an exaggerated version of the elliptical orbit of Mercury, but it's just for illustration purposes. Isolated by itself, a two-body system, just the sun and Mercury, Newton's laws say Kepler's laws, okay? Goes around an ellipse, the sun at one focus, it goes fastest when it's closest, it goes further away when it's, it goes slower when it's further away. Okay, fantastic. But the ellipse would stay completely fixed in space. It would never move, it would never precess, it would never change directions, it wouldn't wobble, it wouldn't do anything. There's nothing in the mathematics that says, oh, by the way, there's a term here that shows you that the ellipse is going to wobble or it's going to precess, okay? Precess is a word that is like when a top is spinning. When it's spinning very fast, you see that the axis stays steady, but as it spins, slows down, you'll see the axis precess, which is to say it's doing this kind of thing. And so the axis is not, the direction of that axis is now what we call precessing, okay? And it precesses through an angle at a certain rate through a certain angle, okay? So what did we measure about Mercury? We measured that the ellipse was precessing, okay? So let's look at this right-hand diagram. If you look at the ellipse here that we're showing, Newton's laws would say that it stays right there forevermore, 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 and never changes. But what we found was that every 100 years, that the direction of this long axis had moved through an angle of 0.43 arc seconds. And I'll tell you what that means in a minute. So that's a very small angle, and we measured that for every 100 years that this angle of the long direction of the ellipse had precessed by 0.43 of these arc seconds. Now, what is an arc second? You know there's 360 degrees in a circle. You take every degree and you slice it into 60 little pie shapes, or arcs, and those are called arc minutes. So every degree is divided into 60 arc minutes of angle. Now take one of those arc minutes, 60th of a degree, and divide it into 60, and that's an arc second. One of those is an arc second. So it's 1/60th of an arc minute, which is 1/60th of a degree. So it's actually 1/3600th of a degree. And we're talking about 0.43 of these angles, of this angle, per 100 years. Now, folks, that is some damn precise measurement, okay? So that brings me to my magic word, precise measurement. I gotta write that down for myself, okay? Now, I've been noticing something. I've been noticing on my video and analytics that the minute I say the magic word, 50% of you bail on the video. Okay, well, I'm sorry to see that, but you're missing out on 50% of what you're paying for. Whether you really like it or not, you're paying for it. Might as well get what you're paying for. I won't harp on you all semester. I'm just, saying it now during this sort of third lecture, and then I'm done with the soapbox. But precise measurement. Okay, so with these precise measurements of 0.43 arc seconds per century, no matter what you did with Newton's laws, in theory of gravity, you couldn't make that happen. It says it doesn't predict it. So I've got some videos here. One's with Neil deGrasse Tyson, and it's some really interesting, fun stuff. This video here, is not linked on Canvas, but it just shows the precession actually in a video. It's very short. And then this one here is about a 4 or 5 minute video with Neil deGrasse Tyson talking about the precession of Mercury and the history of how Einstein figured it out. Of course, he's a much better speaker than I am. So I want you to watch that. There's some key information in there. But basically, people thought that maybe you had to put a planet inside of Mercury's orbit. They called it Vulcan. And the idea was to get then the perturbation from that planet pulling on it gravitationally using Newton's theory to get Mercury to start being perturbed and have its orbit precess. They never could find the planet Vulcan. And then by the time Einstein came along, he was able to make a theory that did predict it easily, piece of cake. And so Vulcan as an idea disappeared, Okay, so Einstein knew that space and time were interwoven, and so he suspected that the interaction between space and time might have something to do with this, because after all, you're moving faster here, so your space and your time are different in your perspective than when you're moving slower out here. And so just from the special theory of relativity, he could tell that space-time had to be doing something, Anyway, it took him 10 more years after he developed his first theory of relativity, the special theory, but he finally formulated his general theory of relativity. And now what I want to do is show you a little bit, just the basic 10,000 foot view on how he came up with some of the ideas for that. There's another video that I have on Canvas too that you need to watch. It's actually, if you like Colbert Show, it's about a 7-minute clip of the Colbert Show where Professor Green comes in and explains some things about general relativity. And so listen to what I have to say and pause my video and go watch the Colbert Show for 7 minutes. And then you can come back and see what I have to say about wrapping it all up, which is important for the exam and the quiz. This last material is important. So, I think Dr. Green mentions this too. The things I tell you in my lectures are not just because I saw them in the videos I show you. I mean, they're common knowledge for physics geeks. Every physics geek knows this stuff. And so, of course, when Dr. Green talks about it on Colbert, it's because he's a physics geek and he knows it too. But it came down to what's called Einstein's happiest thought. And he had it when he was about 27 or so, maybe a little younger. And he said, if I was in a windowless elevator or rocket that's accelerating, and so let's put our rocket in space and accelerate it upward, and that's what we're showing in this diagram to the left here, and it has no windows. I could never tell the difference between that and being in a windowless room in a planet. Now let me go and explain. This is an accelerating reference frame. There's a force of thrust on the rocket. The rocket has a mass. Therefore, F equals ma. The rocket has a force of thrust acting on it, and it has a mass, and so the rocket's going to accelerate. And that means that its speed is constantly picking up faster and faster. This corresponds to, say, time equals 0. This corresponds to 10 seconds later, and this corresponds to, say, or 7 seconds later, and this corresponds to 15 seconds later. For example, so 0, 7 seconds, and 15 seconds. The force is accelerating its velocity so that it's moving at a slow speed here, a faster speed, and even faster speed. So each instant in time, it's going at a faster speed. And so it's going to look like, if you're standing in this elevator, that this ball that's sitting here, if you let go of it, is going to look like it rushes to the floor of the rocket. Now, from our perspective, we can see that the ball is motionless in space, and the rocket floor is rushing up to the ball, So if you let go of the ball some height in the rocket, as the rocket accelerates, the floor of the rocket will move up to meet the ball. If you're standing in the rocket, though, what do you see? You're moving up with the rocket. So the ball's here, it's going to look like it's going down. So if you're inside the rocket, you will see the ball rush to the floor of the rocket. You too will feel the rocket floor pushing on you, and it will feel like your weight. Okay? Now, let's look at the other situation, and that is now you're in a stationary frame of reference on a planet that has gravity, quote unquote. Okay? You're in the rocket, you let go of the ball, and the ball falls with time to the floor. Okay? Now, if the acceleration of the planet, that's to say its mass divided by its radius squared, is equal to the acceleration of the rocket, so that they're both, this acceleration upward is equal to the acceleration of the gravity in the gravity field, you can't tell the difference, okay? So you let go of the ball some height, you see the ball rush to the floor, you feel your weight. To 100% precision of every measurement to date that we can make, okay? And we pushed on this and pushed on it and pushed on it. We cannot tell the difference, okay? 100% precision of every measure we've made. If you're in this situation, you're accelerating and you let something that's motionless there move in that area that you're at, it will look like it's falling or accelerating downward to you as if it was in a gravitational field, like as if you were sitting on a planet. And the same thing, if you're sitting on the planet and you drop the ball, it will behave exactly as if you were in a rocket that was accelerating upward. Okay, we can't tell the difference. Einstein called this his principle of equivalence. It was the happiest thought of his life because he realized now that gravity had to do with the fact that there's no force. It's that we're in a frame of reference like the rocket that's accelerating. Say that again. I'm sitting in my chair here. I'm not moving. What do you mean I'm accelerating? Yes, folks. It turns out we are in an accelerating frame of reference, just like the rocket. Okay, and it's due to the fact that we're in a gravity well. And well, let me get to the next step. Okay. Here we go. Happy thought two, okay? If I shine a light from one side of the rocket to the other side of the wall, okay, opposite wall, the light path is going to appear to bend downwards as it crosses the rocket, okay? Because the rocket is moving up, and so the light leaves at this height, it's going straight, but the rocket moves up. And so therefore the light strikes the wall on the other side at a lower height. But from my perspective inside the rocket, it's going to look like the light beam bent down. Okay, so here's the accelerating elevator upward or the accelerating rocket upward, and the light beam appears to hit the wall at a lower spot than where I'm aiming it because the elevator rose up. And so the curve here depends upon the acceleration rate, and it looks like the light path, in my perspective, has bent. Okay, so in an accelerating reference frame, light looks like it's bending. Okay, so what Einstein realized then is if my drop ball experiment is a principle of equivalency and has to hold, it must hold for light too. Okay, and so he said, if I'm sitting in a room on Earth and I shine a flashlight at the wall, the light path should bend downward and fall lower than where I aimed it. And in fact, this does happen. It's just that this angle is so small, you'll never get to notice it. It is absolutely minuscule, okay? And however, if you were around a black hole where the acceleration is much greater, then the bending can be much more severe. And you might actually, if you were standing on the surface of a black hole, if you could, you might see your light beam actually go down into the ground and disappear into the event horizon. So don't recommend that experiment. So the bottom line is that if you are an accelerating reference frame and it appears to you that the light ray has bent, then it must be true that the light ray is going to bend if you are in a gravitational field. Okay, it worked here for the ball, it should work here for the light. And in fact, guess what? They found it to be true, been able to measure this. Since light beams go straight, it must be that space itself is what's curved and bent. So when you exist in an accelerating reference frame, whatever that means, it's the same thing as saying you exist in curved and bent space. So let's rephrase what I said before. You live in curved space. Okay? So it must be that space is bent in a gravity field and that light just follows the shape of space. So light is your way of measuring the shape of the space around you. Okay. Here is the key to the meaning of relativity, the way I like to say it to people. I think it's the most concise way to say it. Colbert asked Dr. Green to say it in technical terms, and it's really fun to hear him say it. He talks about tensors and metrics and all this kind of garbage. But really, if you had to say, can I explain this to my 5-year-old daughter, I would say the mass of a planet tells space around it how to bend. And then the bent space tells objects around the planet how to move around. So let me say it a little more concisely. Mass tells space how to bend, and the geometry of space tells light and objects how to move. So it tells an apple how to drop. It tells a pen how to drop, okay? That, ladies and gentlemen, if I'd been in a rocket moving upward, I would have thought that the pen was accelerating downward like I was in a gravity field. Now I'm in a gravity field. It's no different than if I was in the rocket. The reason is that I am in an accelerating reference frame, which means I'm in curved space, in curved space-time. Okay, mass tells space how to bend, bent space then tells objects how to move around in space, like this. Okay, that's the last time we're going to do that annoying thing. Okay. So you may have seen this kind of diagram, and when you watch Colbert, you'll see that Dr. Green's going to put out a little, stretched nylon thing and roll some balls around it. It's really quite good. And basically he's doing what's here in this left-hand diagram. Basically you see that if you have a massive object, it will bend space in such a way. This is, again, a schematic. Space does not bend this way, but it does help us understand visualization of it. And so then objects that move around in this space are told how to move by the space. So for example, if you're whizzing in here really fast, you might come down, pick up some speed, and then slow down as you come back out and go on your merry way. And instead of going straight, of course, you go in this curved path. Notice that you're going in this curved path, you're picking up speed as you go down into this funnel, and then you lose speed as you go out of the funnel. That sounds a lot like Kepler's second law, right? As you get close, you go faster, and as you move away, you go slower. Okay, turns out you can take all of Einstein's theory, all of his nasty equations, and you can derive every single one of Isaac Newton's gravity theory equations, because it's a special case of just kind of flattish, normal areas of space-time, and the equations come out and give you all of Newton's stuff. And then from that, you can continue forth and get all of Kepler's stuff. So it turns out that Einstein could predict all of Newton's work, and he could predict all of Kepler's work. And so that was obviously another sign that he was on the right path. Okay, you can have circular orbits. if perfectly circular orbits going around, because the object, if it's not, it doesn't have any friction, it won't lose any energy and it will go round and round and round in the circle forever. Or you could have regular elliptical orbits like we've talked about for planets. And again, as you fall down into the well of the curved space-time, you pick up speed. You're going fastest at the bottom. You come back out, you lose speed, and then you go slow. And then you come back and you fall and you pick up speed. And so you get Kepler's law of planetary motion. Now, we can't see it like this, and we're embedded in the space-time. And in fact, people say it might look more like this when you get around the planet. It's a three-dimensional warpage of space-time that you exist in, not a two-dimensional. But this funnel thing works really well for all its shortcomings. And watch the Colbert video, and you can watch them play with some balls, and they're like children. They have a great time with it. Okay, now the thing that I want to show you was that Einstein's new theory of this warped space-time around masses said, hey, the space-time around the sun is warped. And so that warped space-time is telling Mercury how to move around the sun. And guess what? Einstein's equations say it should move around the sun and such that its elliptical orbit precesses at 0.43 arc seconds per century, right on the bullseye, arrow right on the target calculation that Einstein did. Now, Einstein worked on that mathematics to develop the theory from 1905 to about 1915, 10 years. When he thinks he had the right theory, and he had several theories before that, and then he'd do calculations and realize they were wrong, but then he got a new version of the theory out, where he made some adjustments. Excuse me. And he sat down and he said, okay, can I predict the precession of Mercury's orbit? That first night when he got the equations. And he wrote them down, and boom, they still got the piece of paper he wrote on, and it says 0.43 per arc second. He nailed it. And that was an amazing moment for him. After 10 years of labor, he said that his heart went through his throat. He was so excited he couldn't work on any more physics problems for 2 whole days. And he knew that he nailed his theory. And so that was a very precious moment for him and a very big moment in science. Now let's talk about the paradigm shift, ladies and gentlemen. We had a paradigm shift from Newton. We don't have absolute time, and we don't have absolute space. And hopefully you watch those 2 videos that show that, and you don't have to understand every part about them, but it's important you get exposed to them, because it does go into your brain, and you do learn some things, even if you don't really understand all that math, the little bit of math they showed. But the space-time diagram is a paradigm shift in our understanding of how we look at the world. We see these events that have space-time coordinates. And of course, maybe you saw where those 2 things on the train go ding, ding, and the other ones went bzz, bzz, and one person saw them go off at the same time, and the other one saw them go off in a certain order. And it depended upon from whose frame of reference, what order you saw everything happen in. Now that's pretty spectacular. So if you didn't watch the video, you got to go back and watch that video of Galileo and Albert Einstein making these measurements and how it shows that space has to be contracted and time has to be dilated. I know some of it's complicated, but some of it's very, very also well done and accessible. Okay. So space-time now is a continuum. It's 4-dimensional entity of space and time together. And now we have another paradigm shift that you don't have gravity. Okay, so let me tell you something that you gotta walk away from with this class and say forevermore. Repeat after me. There is no such thing as gravity. There is no force of gravity. There is no force of gravity. There is no such thing as a force of gravity. Newton, for everything in his math that describes the world so accurately, is not the actual picture of what we think reality is. The math works, but it's not a picture of the world as we see it today. In his day, he saw a force that acted from the center of the sun to the earth, or from the center of me to the center of the earth, that kept me bound to the earth, or kept the earth bound to the sun, okay? That doesn't exist. Masses warp space around them, and the warp space tells objects where and how to move. That's a very different thing. And what I'm going to show you in the next slides or two is some of the predictions that came out of this that you could never make or never think about if you were just thought Newton's world was the way the world was, okay, his vision of the world. Okay, so this is a paradigm shift, and now I'm going to tell you how that paradigm shift was a can opener on the human mind and opened up a whole new universe to us in the last 100 years. Okay. So everything follows curvatures, even light, and so even light rays are curved past around stars and galaxies. That's one of the first predictions that we're going to talk about. Okay, here we are. 100 years of things predicted by Einstein's theory of general relativity, warped space-time, to explain gravity fields. The first thing he solved right off the top of the bat was the precession of Mercury's orbit. His theory predicted that the universe should be expanding or contracting. In 1927, Edwin Hubble noticed that galaxies are moving away from each other, and that the further away they are from us, the faster they're moving away from us. This is due to an expanding space-time. Boom. Check number 2. The bending of light. In 1919, okay, we'll talk about this a little bit more, an experiment was done which was able to measure the bending of light rays around the sun. Okay, the sun's gravitational influence was the warp space-time, the light rays bent around the sun. Something very bizarre called gravitational lenses. I don't even know. I'll have to explain this to you in some following slides, but that wasn't really solidified until the 70s. And of course, now we use gravitational lenses as tools. We literally use them like they're a new lens or a new window on the universe, and we're able to measure all kinds of new properties about the universe using the fact that big masses actually bend light and focus it in this way. So again, a new window that became a new phenomenon. Once we verified it exists, we turned it into a tool to learn about the universe. Black holes, 1965, they were first discovered. They were actually predicted, it took about another 10 years to predict them from the theory in 1920s by Carl Schwarzschild. And he worked through Einstein's equations and predicted the black holes. So not all of the predictions that came out of Einstein's theory were from Einstein himself. And then those were discovered in the 60s to probably exist for real. And then in the 70s and 80s, we just solidified them. Now you've probably seen we've actually imaged a black hole for the first time, and fantastic stuff. So if you haven't seen that, you should Google it, image of a black hole, and read about it because it's fascinating. You also get something called relativistic beam boosting around certain types of objects that cause them to be super bright and super luminous. And so that was discovered in the 60s. You can't explain these super bright objects or these bursts without them. And then one of the other things is that time can run slower when space is more warped. I'm not going to be able to give you a slide on that, but I want to talk to you about that for half a second. Okay. How do we figure this out? The most definitive measurements came in the 80s with the space shuttle. You basically put an atomic clock in the lab next to another atomic clock, and you calibrate them so that they're set at the same exact time. You synchronize them. You put one in the space shuttle, and you fly it up into Earth's orbit, okay? You go up there for about 2 weeks. You bring the clock down that you took up there. You put it next to the one in the lab, and what do you find out? The one in the lab ran slower than the one in the space shuttle. Yep. The astronauts moved through time faster than the scientists in the lab. Okay. So this has to do with where you are in the warp of space-time. If you're on the surface of the planet, you are where it's more warped. Okay. And so the more warped or curved the space, the slower time runs. As you go up in the space shuttle, you're further out from the warp. You're in a less, not as severely warped space, and time will run relatively faster. So if you want to live a long time, you should go live at the lowest altitude on the planet, say down in Death Valley or whatever, below sea level if you can, or heck, go down to the bottom of the Mariana Trench in the ocean and live down there. You will get yourself a microsecond extra of life over your 100-year existence, but we've measured it to high precision. Okay, gravitational redshift. This is a really bizarre thing, that light that might work its way out of an area near a black hole. It might come out blue, and it might be emitted as blue light, and then as it works its way out of the gravity well, if you will, of the neutron star or black hole that it's near, the light will get redder and redder and redder and redder. It loses energy. It loses energy to the space-time configuration around it. And this is called the gravitational redshift, okay? That was predicted by Albert Einstein and measured. You can't have any of these things in Newton's theory. They just don't exist. You can't even predict them. If you can't predict them, if it's not in the math, you don't see the universe having these things in it, you can't learn about it. And if you go verify they exist, then you can turn them into tools to learn more about the universe, which is what we've done in every single one of these cases. Okay, gravitational radiation. Okay, whoa, what's that? Well, it's related to gravity waves. Gravity waves, wow, what's that? Ripples in space-time, okay? You know, like you drop a rock in a pond and you get ripples that move out. Well, if you have something like two black holes that collide, they're causing a lot of perturbance in the warp of space-time around them, and they ripple out across the universe. And so I've got some videos on that. I got a few of them because this was the holy grail of Albert Einstein's theory. Everything else had sort of been found, but we kept saying, are gravity waves there? Because that's a big one. If you get ripples in space-time, and those ripples behave the way that they're predicted to behave, then you really have another major feather in the cap, if you will, verification of one of these theories' predictions. So you can see the process from our little flow chart. Make a prediction, do an experiment, it confirms it. Go to the next prediction, it confirms it. Go to the next prediction, it confirms it. That's Albert Einstein's theory. Unbelievable. Every single one of them, right on that circle of prediction, check mark, found. Okay. So I love talking about this. So we'll talk a little bit about bending of light and gravitational lenses, and then we're going to talk a little bit about gravity waves. Okay, so here's the slide that talks about the bending of light. So you can see here if Hubble's orbiting around the Earth here and it looks past a star, say it could be the sun for as far as we're concerned, and you get this warpage of space-time around the star. Now, there might be a star that's way back here off to the side here. This is the, I'm saying it wrong. There might be a star that's here that's actually behind the foreground star, what we'll call the intervening or foreground star. We'll call this the background star. Its position really might be here, and light's coming off of it in all directions, but certain light comes off in such a direction that after it gets bent, it ends up heading in our direction. And so when we look at the angle at which the light's coming into our telescope and project it back outward, we think that the observed star is over here. So on the sky, the star might be here, okay? but the light got bent, it's coming at me this way, and so I think the star's over there. And I see it in the sky over there because that's where the light direction's coming in. Okay, so in 1919, about 4 years after Einstein published his theory, a British astronomer, Arthur Eddington, went halfway around the world and took an image of a star field in a location in the sky where a solar eclipse was supposed to happen. Solar eclipse means that the moon blots out the sun during the day. And what happens when the moon goes between us and the sun is it blocks out the sun and the sky goes dark. And so you can take another image of that same spot, though the sun now is in there, but its light is being blocked from your photograph and it's not blinding you or making the sky turn blue. So he repeated the photo during the eclipse, and he observed the positions of the stars and found out that they had shifted. And the measurement, the prediction of how much they shifted was exactly the number predicted by good old Albert Einstein and his theory of general relativity. And this is what shot Einstein to international stardom and fame immediately, because now the world knew he had supplanted Sir Isaac Newton. And if you're gonna, basically pick up Isaac Newton by the wig and throw him in the garbage can, the world's gonna take note. So that's what happened. And his theory replaced Isaac Newton's, which was the achieving, crowning pinnacle of all theories by any human ever. And now we have a new crowning achievement pinnacle. Again, I'm not talking about quantum mechanics, which is another whole story and fascinating. So if you look at the universe, you can think of it as sort of a space-time fabric. And as galaxies, when the light as galaxies propagates across the universe, the warps of space-time that happen because of mass concentrations, which they're not showing in this diagram, but you could say there's a mass concentration here, and the light then will move around it, and it doesn't follow a straight line as far as we see it, but as far as the space-time geometry is concerned, it does follow a straight line, okay? And it goes at a constant speed. So throughout the universe, massive objects warp their space-time around them. The warped space-times tells objects, including light, how to move through that space-time. And so the light follows the curvature, and then the geometry, it turns out when you combine all of the different massive things in the universe together, that their distribution actually dictates the overall curvature of the geometry of the entire universe. So the entire universe itself has a geometry that's curved and things like this. And it turns out it's pretty much flat, that we found out on average, but it has these undulations in it. Okay, gravity lenses. Again, something that became a powerful tool. All right. So light rays that take curved paths through the universe when they go past massive galaxies. Okay, so here is a foreground galaxy, a very massive foreground galaxy. We are at Earth, and here is the background galaxy. And so the light from the background galaxy is going off in all directions, but some of it goes off in a direction such that after it passes this massive warped area, okay, it gets redeflected toward our telescope where we just happen to be. It just happens to be a coincidence that that particular light ray came off at an angle that by the time it followed the warp of space, got redirected and pointed at our telescope. And of course that happens on the other side. It happens all around it actually, because the light that's coming up and then going down too. And so when you look at the image that you get on the sky, this is the image that you get on the sky, you can see that the center galaxy here is in the center of your frame. But since this light is coming at you at this angle, it looks like that material is over here on your sky, and it shows up there in your image. And the same thing with this light here is coming in at this direction. And so when you look at how what it looks like on your photograph, it seems to be over here projected on the sky. And so this redistributes the light and amplifies the light from this object. And so we can actually study two things. We can study this galaxy spatially in detail, and we can also study the shape of the space-time around this massive object here. And so we can use it as a tool to actually study the warpage of the space-time around these intervening galaxies. And that's one way that we've discovered something called dark matter, which I'm not going to get into in this class. Okay, now this would be another example of this. Looking on the sky, this is a true image, not a cartoon like this one. And you can see here's the foreground galaxy, and then here's some lens background galaxy. And this is where it looks like on the plane of the sky, even though this galaxy is probably pretty much right behind this galaxy. We see it in this arc. And so it's really great because what we've done is we've resolved some of the shapes that exist in that galaxy, so we can study a spatially resolved image of what would otherwise be a point source looking object. And we can study the warpage of the space-time around the foreground galaxy. So a very powerful tool. There's more to it than that. I'm just giving you the ABCs of galaxy lenses. Okay, just an aside, and I just want to read this to you because this is really important. As much as I've touted how amazing relativity is, general relativity is, it turns out that there's a fly in the ointment. And it turns out that every prediction that general relativity makes, okay, has been verified. But once again, we have discovered things in the universe that general relativity, that a theory of warp space-time should address and predict, but they're not predicted by general relativity. You see what I'm saying? The predictions it makes, all of them have been found to be true to the precision of every measurement we've made. But we've made measurements, other measurements, particularly in quantum mechanics, that tell us that a theory of space-time should predict those things too. And general relativity can't predict those things. It just doesn't. Okay, so it's also an incomplete theory, as powerful and as amazing as it is. So I just want to read this aside to you. Even though general relativity has passed every test based on predictions, guess what? We have observed stuff that cannot be explained by general relativity. Most of these observations are on the scale of the very small and involve quantum mechanics. Scientists know that general relativity must be unified with quantum mechanics in order to have our theories be even more precise about the universe that we observe. What will that theory look like? What will it predict that we cannot even think of as questions today? Or what phenomena will it open our eyes to that we would never imagine exists out there? Just like relativity, general relativity opened up our universe to gravity waves, gravity lenses, gravitational redshifts, all these other things that explain the precession of Mercury. Could this new theory of a quantum gravity or a quantum general relativity, quantum space-time basically, take us to the next level? And in fact, might we learn to build faster than light spacecraft from it? Might it take us to a whole nother dimension of existence? And I don't mean like dimension as in space-time, but a whole new level. So the last holdout in our century was the gravity waves. In fact, all these other predictions had been found before the year 2000, but what about the gravity waves? And it turns out that the gravity waves were discovered in 2015. An amazing discovery where they've measured undulations in the space-time continuum that are smaller than 1,000th of the width of a single proton. I'm going to just let you think about that for a second. 1,000th of the width of a single proton. Almost unfathomable. Hey, we humans, we're getting pretty good, well, in my opinion, okay? But still, it's pretty amazing what we're not good at. Look at the world today. Okay, so what happens when black holes collide? Because that's really, if you're going to be able to see anything, it's going to be two black holes colliding. You know, supermassive object one, supermassive object two. They come together, ripple, ripple, ripple. You know, you're not going to see when two flies collide. That's not going to. It's not enough. You know, warpage of space time to even really make detectable waves. Sure, it makes some waves, but it doesn't make detectable waves. You want detectable waves, so you got to go after the big juicy waves first, the tsunamis, if you will. All right, so I don't have a lot of writing on this diagram, but let me explain it to you. We've already talked about how a planet like the Earth will warp the space-time around it. Okay, there are black holes that orbit each other, and that's what this area here is showing. Okay, I think I can actually zoom in a little bit. So you've got the two black holes here, and they're orbiting each other. And as they orbit each other, they're causing these little bit of ripples in the space-time continuum. You can see the dramatic warps as you get close to them, okay? As they go faster and faster, they'll spin up and go faster and faster and faster, and you'll get literally sort of this whirlpool fanning out of these ripples, okay? All right, so what happened was we built this detector called LIGO, and it's two right-angled arms, and you send light up and down them. Now, I'm not going to explain it any further than that because there's those two videos that I'm giving you on this, and the one of them, they do an amazing job of explaining how this experiment works and impressing upon you how precise and accurate, and it's 20 years in the making plus. So, you know, you got to give it up to these people that did this work. You know, and this is a human lifetime working on one experiment in the hopes that maybe they'll find one of these waves pass through the Earth that they could detect it. Most of these people could have gone to their grave, worked on this, and never made a detection. It's a dedication and a passion to learn about the universe. These are examples of three waves that were detected. And it's kind of like these plots look like one of those seismic earthquake diagrams. But as the waves move, they basically stretch and contract these arms from one another. Then the light beams they send up and down will interfere with each other in a way that they get brighter and dimmer and brighter and dimmer at a certain rate, the rate that the wave moves through, and it causes this up, down, up, down, up, down intensity pattern. And so it starts out very, very powerful at first, and then it decays with time, and the ripples become further apart as with time. And so you see that the signature is exactly predicted by models of these coalescing black holes. Those models predicting what the wave pattern should look like when it passes past the Earth were exactly what was measured in the instrument. Again, check, it's just right on the money. Now, what's really cool is that if you could hear these, because the frequency of this vibration is actually in the audio part of your spectrum, and they have audio versions of them online. I'm not going to make a fool of myself and make it sound, but they have audio versions of these. You can Google, you know, audio sound of a gravity wave, and you should get a little sound file that you can click on, and you can hear it go by, and it's pretty cool. This again is an example of the experiment. I didn't want to go to it in detail, but this diagram is here for anybody who wants to sit and look at it. Particularly after you see the video, you could come back if you're really interested and take a look at this. But you've got light beams going this way, back and forth 40 times, back and forth 40 times. These are 4 kilometers on the side. And then you eventually, after the 40th pass back and forth, you let them come back together, and they either add constructively or add destructively. And you can tell whether these lengths have changed with time or vibrated with time, okay? And then here's the black hole of this candidate. So the first time they detected one, if we're here, the first one they detected was 1.3 billion light years away. Now that's an incredible amount of distance. That's further away than, you know, the largest cluster of galaxies that we live next to. And I'm going to describe all that in the next chapter. So anyway, it was discovered on September 14th of 2015. This is the gravitational wave. This is the number of the file. It was 62 solar masses, or 62 times the mass of the sun. And the diameter of these black holes is about 300 kilometers. So this happened. This was the first one that was detected. The second one was 1.4 billion light years away, 21 solar masses. It was smaller. And this was discovered just after Christmas in December of 2015. And so it was nice to get a smaller detection. First of all, it's weaker, so it's harder to find, and they still found it. And then, of course, it has different behaviors because the masses are smaller. And then the third one they detected was 3 billion light years away, twice as far as the second one, 50 solar masses, fairly massive. And so all of a sudden now, we have a new window on the universe. Like I said with the gravitational lenses, we found them, and then we learned how to exploit them as tools. We have now found gravitational waves. We can measure the ripples of space-time. Guess what? We are going to turn that into a tool, and we are going to apply it. So come back in 20 years and find out what's happened with what we call gravitational wave astronomy. Okay. These are the two must-watch videos. You can link to them here in the notes, or you just go on Canvas because they're amongst the videos. I think one of them is called "Have Gravitational Waves Been Detected?" And that's the first tentative detection here before it got released. But, you know, it was kind of through the grapevine before it was released as real detection. People got wind of it, talked about it, and then it all explains the gravitational wave stuff real well. And then the second one is the true announcement, discussion of the gravitational waves. And if you become a nerd and you want to watch this PBS Spacetime videos, they have another one called The Future of Gravitational Wave Astronomy, which I didn't link to because I've already linked too many videos. Okay. Now, let's just talk a little bit about that future, though. And that is something called ELISA. And ELISA is a series of satellites. And this is how they work. It's 3 satellites that are located at 3 locations around the Earth. And they're located at the radius of the moon's orbit. So they're going to co-orbit the Earth in the moon's orbit. And they're going to orbit in these they're called stable positions, Lagrangian points. You have to be a physics major to sort of understand what that's all about. But there's these stabilities in the space-time warpage where you get this little dip where you can, if you go there, you can sit in it like a little puddle in a pond. And so if we put the spacecraft in those 3 Lagrangian points, they'll stay there, they'll orbit in lockstep with the moon. And so we'll fire lasers amongst them. And so if a gravitational wave comes through here, it will change the distance from here to here just a little bit. It'll change the distance from here to here a little bit, and the distance from here to here a little bit. And we can measure that through the pulses of the constructive and destructive interference of the light. Here's what one of these satellites is going to look like. Now, this is a weird diagram, but this is the sun, and this circle now is the Earth's orbit, that sort of purple circle. And this is the one location. So if the Earth was right here, forget all this other junk for a second, if the Earth was right here, this would be the location of the 3 satellites, and this would be the moon's orbit. If you come back, say, a month later, the Earth will be over here, and this would be the moon's orbit around that Earth. You come back another month later, it has moved over here, et cetera, et cetera, et cetera. And so basically you can see that as the Earth orbits the sun, the orientation of these change throughout the year. And so it's basically like having a moving laboratory that goes around the sun, and we should be able to detect with great sensitivity gravitational waves again and again and again as they come past the Earth. Okay, so maybe someday you'll go to the moon, and you'll get out your little telescope and you'll be able to see the ELISA satellites on the Lagrangian points. Ta-da! I bet you're so happy. We're at the very end of the video here, but you've got to listen to the recap, or at least read the darn thing, because this is important, because this summarizes everything for our next step into the cosmos at large, okay? What did we do? What was it I want you to understand we did? We used a historical perspective to learn science is an imperfect human endeavor and to some degree an art form. And it's founded on philosophical principles that reflect the culture of society at the time. And that has developed. And it also feeds back on it and influences the future course of culture and society. And I don't mean just the development of technology, but I mean philosophy, political systems, and economic systems. The whole idea of the founding of this country is really stems a great deal from the Newtonian view of the universe, which then made a view of economic systems, which then made political systems. And then the philosophy, the argument of is there human fate or is there free will? All those arguments that happened for centuries, okay, all came out of that. So it's a process, and it's a uniquely human thing. You should not think of humans as we've always arrived and always been like this. We have slowly developed these things over time. If you really want to understand who you are, you really want to understand what we are and what you exist in, you have to learn about the history of humanity. You've got to, otherwise you have no clue that why the world is the way it is. And therefore you really don't know how to act on where to take the world in the future. And that's really our crisis right now, is we've got 8 billion people on this planet and we don't know where to take it. We don't know where to take it because only like 5% of the people really know what we're doing with ourselves, where we've been and how we get there, and can look back at it with a perspective of understanding what's going on. The rest of the 95% of the population, almost 8 billion people, are just creating noise in that sense, as far as the directionality of humanity. Now, that's not to take away at all the love and the families and the altruism that should be in humanity, the beauty of just being alive. I mean, you are just as valuable in my view of being alive if you didn't contribute to society and you just like to live on a mountainside somewhere and be on your own. That is a beautiful thing. You are a living being. It is just as beautiful as if you were, say, Albert Einstein, okay? But I'm just saying, as far as like our collective social consciousness of where we're taking the world, you have to know these things. That's why you're taking this viewing the wider world class, okay? Well, I really could be on my soapbox sometimes, but I hope that some of you, or one of you at least, is still listening, okay? Maybe you could pop me a Canvas message. Yeah, I'm still listening. Good soapbox. Well, you don't have to go that far. Okay, for the most part, it's a very painful process. There's a lot of work marked by this creative thought. It's small incremental process that we usually do, such like Ptolemy did, and we call it refinement. Okay, we sort of just add a little bit of more layer to what we're looking at because we see the world a certain way, we can't get over it, so we pile on with that theory and refine it. But once in a while, we go beyond that. So anyway, often these theories, almost always, we're smart enough to know that they're incomplete, that they have flies in their pudding. And so they either make some incorrect predictions or else they cannot predict phenomenon that we've observed, such as Einstein's theory of relativity. Every prediction, 100% found to be true. We've also found things that it can't even predict, okay? We call this situation tension, like the tension between Maxwell and Newton that Einstein resolved, and we paradigm change, okay? So tension is good. Tension is the area we like to focus on and learn from. Occasionally, this tension between the observation and the theory will yield a revolution. The development of a new theory accompanied by a profound change in our understanding, such as the difference between Newton and Einstein, and sometimes the theory completely replaces our picture of reality. We call this a paradigm shift. So I've taught you about refinement, tension, and paradigm shift. Science is rich in history. It teaches us that we can never know the actual truth of this universe or have a final and complete and total correct theory. Science is just a work in progress. Science is a creative human endeavor in which we continue to improve our understanding of nature and the universe. That is one of the most, cliche, boring sentences you could ever imagine, okay? Science is the creative human endeavor in which we continue to improve. Okay, you can either look at the world that way as a bunch of definitions that are boring that you memorize, or you can look at the history and look at it and be like, wow, once I learned that story, it is a creative endeavor. It is a painful process. You see, if you just memorize platitudes and facts, life is boring. Get into it. Learn the story. Learn it. Enjoy it. Become richer because of it. So that ends our How to Science, and that ends our story of modern science. And one of the directives of this course is to teach you how we do science, okay? We're going to now move out into the universe in our next segment, and we are going to talk about 13.6 billion years of cosmic history, and we're going to talk about expanding universes and might mention dark matter and dark energy, and I'm going to show you how stars form and how we are connected to this process that exists over billions of years. And we are just one little pinpoint in time and space in this major process. It's going to be a very, very broader perspective. It's not viewing the wider world, it's viewing the wider universe, okay? That's where we're going. And so hopefully you're still with me and you're gonna hopefully still want to grow and enjoy that area. So until then, you know the homework assignments, you know all the things to do, and I'm not going to bore you with it. And I wish you well, and thank you for listening, and thank you for listening to my soapbox and soap opera types of statements. So anyway, take care. Maybe I'll see you at office hour. Thanks.